In our previous videos, we were talking about probability distributions. In the next couple of videos, we're going to talk about sampling distributions. But first, a joke. So a famous statistician would never travel by air because he had studied air travel and estimated the probability of there being a bomb in any given flight was 1 in a million. And he wasn't prepared to accept those odds. One day, a colleague met him at a conference far from home and said, "How'd you get here? Did you come by train?" And he responded, "No, I flew." And his colleague said, "Well, what about the possibility of a bomb?" And the statistician said, "Well, I've been thinking that if the odds of one bomb are 1 in a million, then the odds of two bombs are 1 in a million times 1 in a million. That's a very small probability and one in which I can accept. So now I bring my own bomb." So we're talking about probabilities and we're talking about probability distributions. And we want to carry on that conversation by moving on to sampling distributions, continuing that discussion about a probability. So we've looked at techniques to describe graphically and mathematically data. And ultimately, we want to take information from our sample and we want to make statements about the greater population. So we take a sample. However, there are fluctuations in the samples. Each time you take a sample, you get different results. So we can't directly take the results of any one sample and extrapolate them to the greater population. So instead what we do is we take our sample and we match it to a theoretical distribution. These probability distributions we've been discussing in our previous videos. So what I talk about now is taking that sample and the sampling fluctuations that we get. What do we do with that variability from sample to sample? So I want to make a statement about the population, but we do not want or cannot examine all the objects in the population. We've talked in our previous videos about how a census, where you contact everyone in the population to get information, is just too cost prohibitive, too time consuming, or maybe the type of study we're doing creates damage to whatever we are investigating. So maybe in order to analyze the plant, we actually have to take it apart. Well, we wouldn't want to then do that to every single plant or there'd be no plants left. So we want to take a sample, a portion, a part, a subset of the population and extrapolate to that greater group. And so we need to recognize then that each time we take the sample that it's going to be different. So let's suppose, for example, we're looking at computer chips. You want to examine them. Let's say you're a company that manufactures them. And you take one sample and you find that there are 5 defective computer chips in a batch of 20. Well, does that mean that there's 25% of all computer chips are defective? So we need a way to understand how each time we take a sample, we're going to get a slightly different group. So the chips we take will be different each time. So you won't always get 5 defective computer chips in every batch of 20. So we need to define what is called sampling error. And sampling error is the difference between a sample statistic and its corresponding population parameter. Now, sampling error happens by chance because one particular entity might end up in the sample or not. So sampling error is not a mistake, but it's due to the variation in the population. So one of the reasons we want to have a sufficient sample size is so that we capture that variability in the population. And we've actually talked about sampling error already. You'll recall, where's the beginning of the slides? We had some videos about designing a research project and we talked about developing a sampling plan. So there you would define your population of interest and choose a data collection method, whether it was going to be a survey or a focus group. If it was going to be a survey, are you going door to door? Are you sending out an email? How are they completing your survey? And we identified a sampling frame. So what is that group that we are looking to take our sample from? And what method are we going to use for sampling? And so I'll just quick scrub through here. We talked about probability and non-probability samples. And we talked about different sampling methods depending on whether you can get a representative sample or whether it's a non-representative sample. So if we are going to have a sample that represents the population, we're using systematic, stratified, cluster, or simple random sampling methods. But if we can't obtain a representative sample, then we are doing a non-probability sample, which limits our ability to do that extrapolation to the bigger population. And so we have to recognize that. Those are convenience samples, snowball, judgment, and quota. Now, ideally, you want to have a probability sample because you can extrapolate to the greater population. We can actually then state explicitly what the amount of sampling error is. And sampling error is that difference between your sample statistic, for example, the average of your subset, and the population average. Okay. Now, sampling error occurs because of that variability in the population, and that is different from, say, measurement error, which we've talked about previously, which are limitations due to the tools you are using to collect the data. So refer back to the videos on measurement error in terms of that additional error that can be added there. Right now, we're going to be focusing on sampling error. So as we look at sampling error, we're looking at the difference between a parameter and a statistic. A parameter is a summary characteristic of the population. So it could be the proportion of adults who are left-handed, the probability that any baby who sleeps with a nightlight will have myopia or nearsightedness at age 20. It could be the difference in the average incomes of men and women in the same profession. So parameters are summary characteristics of the population. When we talk about summary statistics, think back to our measures of central tendency, right? Mean, median, mode. And we also looked at frequencies, which can be turned into proportions, percentages who fall into certain categories. We compare that to a statistic, which provides us the information about the sample. A parameter makes some assumptions. Parameters are fixed, they're unchanging values. So if we go back to some of our examples here, the proportion of adults in the world who are left-handed, at any moment in time, that percentage of left-handed adults is fixed. Okay, now if we take a sample, a group of adults, and figure out if they're left or right-handed, one sample might tell us that percentage is 30%, another sample might say that's 25%. So sample statistics, so a summary, like the proportion of adults in the sample who are left-handed, that can vary. But the parameter itself that we're trying to understand, it is assumed to be fixed, at least for any moment in time. So it's fixed and unchanging. So we're trying to get to what is that underlying parameter. We don't know what it is unknown. We are trying to estimate it with our sample statistic. And the challenge we have is that because of variability in our population, as we grab subsets to be our sample, that sample statistic is changing. Whereas the parameter it's trying to estimate is not. Okay. The challenge we have is the parameter is not known. Now, if we did a census, we contacted everybody in the population, we could know it, but there's reasons that we are not contacting everybody in the population, as we just discussed. Okay, so we'll never have the information necessary to find the exact numerical value of the population parameter, but what we're trying to do is set up good statistical techniques so we can make a really good guess with our sample statistic. And part of that is recognizing that your sample statistic, your average or your proportion, like our proportion of adults who are left-handed, will change with each sample. And so that's why we create a sampling distribution to better understand that variability from sample to sample as we're trying to extrapolate to that population parameter. So our statistic is going to be from that subset. It is from our sample, and it's going to try to estimate that unknown value of our parameter. But because every time we take a sample, we're going to get a different group within that sample, it'll give us a different statistic. So the proportion that are left-handed Depending on who you grab to be in your sample, it's going to give you a different percentage. So sample statistics are random variables. They are going to vary from sample to sample. And because they are random variables, we can describe them with probability distributions. So that's why we're here in these videos talking about sampling distributions. We're trying to extrapolate to the greater population, but we recognize that samples are going to give us different results because they don't have everybody that's in the population. So a sampling distribution is the distribution of all the possible values that can be assumed by some statistic. So if we're looking at proportion of left-handed, every time we take a sample, we get a different percentage. The sampling distribution will show us that range of percentages of left-handed. Maybe they range from 25% in one sample to 60% in another. Do we have a mean, a median, a mode for these different percentages? If we took a different sample each time, we get a different percentage. What does that distribution of those percentages look like? Or if our sample statistic and our parameter is an average, what's the average age? Every time you take a sample, you get a different average age. What is the min and the max? How much variability? Where does it tend to congregate? What does that distribution look like? So the sampling distribution is the probability distribution of a sample statistic.